stream live. Doopy 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 doo. Doopy 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 doo. Alright, there's intro music. Hi, I'm Blades. And, yeah. What's this about? Multiplication experiment. I woke up this morning with an idea of how advanced computers have become. I was going to do a talk about it, actually, one of these Sunday talks about how advanced computers are today and how we made them wrong. That would be the basic premise of the talk. Where did we go wrong? And then I thought, well, how would I prove that? I'd have to come up with an experiment. And this is about the experiment I thought of this morning. It took me 10 minutes to think of this experiment, so I don't know whether the experiment's going to work. We're going to find out. Well, I do know if the experiment works, but the point of this is that I already knew what the result was going to be before I performed the experiment. So is this confirmation bias? Yes, it is. This experiment will confirm the bias that I believe we made the computer wrong. Shall we have a look at how it works? I think we should. You can tell at the moment that I don't trust my internet connection. There's a thing. I don't know if they're still working on it or not. I don't really care, actually. I'm just going to try and do live broadcasts and, well, we're going to fail, aren't we? I guess. I've got a cup of coffee. Cool. So how's this experiment going to go? Well, we're going to multiply 2 by 2, and then we're going to multiply 0.2 by 0.2. And what are the expected results? Well, 2 times 2 is 4. 0.2 by 0.2 is 0.04. Because it has to go down as well. It has to get smaller, whereas anything above the decimal point has to get bigger. Right, as long as we understand that about mathematics and that is true, then we can do the experiment. So I spent an awful lot of time this morning writing a program called multiplication. And it's a very, very detailed program which minimizes anything else that could influence the result. The results that we do get, integer multiplication, result equals 4. Floating point multiplication, result equals 0.04. Oh, it agrees with us. So let's have a look at the program. It's a big file. We can get rid of the application output. There you go. So this is the integer multiplication, and this is the floating point multiplication. As you can see, I've done exactly the same each time. So 2 times 2, 0.2 times 0.2. So what's 22? Come on, what are the results? You should know the results. Let's pop them on the screen. So, as you can see, I spent a whole 10 minutes writing the program, if that. Okay, we get 484 and 0.0484. Hold on a minute, there's something recognisable going on here. There's a pattern going on, which we could make an equation out of, perhaps. Mathematics seems to be doing something which we recognise it should do. And these are advanced computers. The computer I'm using here is less than a year old, and if you were to purchase it in the shops today, in sterling, in the United Kingdom, it would cost you around about £3,000. A lot of money, if not more. And I'm not joking either. It's a very expensive computer. It's state of the art, very much so. This is not a gaming computer. This is a working computer. It does play games, and it does it very nicely, but that's beside the point. The results we're getting, we agree with. All right, let's change the numbers. We need two different numbers first, don't we? So let's put a 5 in front of... let's put some odd numbers in. So let's put a 3. I think this will mess it up. Yeah, we'll put a 3 there. We'll put a 5 there, which means we've got to put a 3 there, and it has to be exact this. What happens now? I don't know what happens to this number. Well, well, well. Isn't that interesting? What, Poppy? Look at that. Come here. Now, I know something about computers that people don't know today because it's not taught. It's not in schools. If you take computer science, they might mention it. They don't dwell on it. But there's something about computers which is, I say, we made the computer incorrectly. Babbage's idea was correct, but the implementation of the idea is flawed. And I'll show you. Because this is doing what we expect, 4 to 0.04. 484.0484. 168084.168084. Oh. It's working. But there is an equation that you can derive out of this, but I don't really care about that. I'm not doing the maths. I don't really want to be a mathematician today, but that's what interests me about this, is the mathematics behind it. Let's put these two numbers in, which I've commented out, because these are the two numbers that I thought of this morning whilst I was making my first cup of coffee of the day. And my first thought was, we can't use these two numbers in this experiment because they don't work. And then I thought, well, hold on, I'll have to prove that they don't work, so I put these numbers in first. Look what happens. Oh, they're not. 122, and it's 0.124. We've just broken mathematics, have we? Well, we've broken the equation that would make these true. So what have we done? Now, I knew that these two numbers wouldn't work before I even typed them into the experiment, which is why I'm showing you. And these two numbers were designed on a simple principle of showing that computers cannot multiply. Well, they can, because the integer multiplication result is correct. And I know it's correct. But what about this floating point multiplication result? Is that correct? Well, do the multiplication, find out. Is the answer. What is the correct result? Well, you'd have to do the multiplication longhand, wouldn't you? So you'd have your 5 times 2, which gives 10. That gives you your 1 and a 0. You have your 3 times 2 and your 1 times 2, don't you? I don't do maths that way. So what would happen if, let me just get rid of this one a minute, if I put in 0.200, whoops, I'm putting points in, aren't I? 200, and then we'd have to put a semicolon and a couple of backslashes, wouldn't we? Yeah. So let's pop U to 200. We have to keep it the same top and bottom, obviously. Just to make sure that I'm not falsifying these results. Oh. The 1 and the 0 is the same, and then it's a 4 and a 6. Which one's correct? $200 times 531 is 2 times 531, and then a couple of zeros added on. So it's 2 times 5. Oh, I've got 521 there. Sugar. Sorry, my bad. No, it should be 521. It's me. Is that why it was all going wrong? Probably. I'd made a mistake, maybe. Let's just run the numbers again. Oh, thank God for that. No, it works. Let's go back and make sure now that we've corrected our error. This doesn't work. Make sure they're both the same number this time. And I bet it works now. I've messed up. Hope so. It does. Oh, thank God for that. So, a modern computer can do that calculation. But in truth, it can't. I'm going to check something, because I know that there is a calculation you can't do. So I'm going to put 2 times 35. We know the answer to this because it is easy. That's 70. 2 0 0. So I've disproved myself already, which is fantastic. I love it when I disprove myself. We got a negative. Wow. 35. So that's 0.07. Because there's these are both floating points. So I'm expecting 70 and 07. It should be reflection. It's a reflection around the decimal point. That's what I'm expecting. That's the mathematics behind it. What do we get? What do we get? Let me make sure I've got the numbers in right this time. Yeah, perfect. Do it. And we get it. Now, I know that the computer cheated to do that. And there's something interesting to think about. I know for a fact that that is correct. And I know for a fact that a computer can't do that. Why? Because a computer is in binary. Try and put 0.07 in binary. Try and work out how they did it. And it's all to do with how a computer stores the number. It has to store it in a binary format. If I'd chosen a smaller number, this would have been a lot easier, wouldn't it? I think I'm going to write another program and see if I can get it to error. I don't think I can because they've put an extra chip in, haven't they? What is happening here is there's a program running alongside your CPU in a maths coprocessor, or circuits on your CPU that are correcting the output. Now that can be hardwired into the chip, or it could be a program within the calculation model of whatever language you're using. Where that program is somewhere, but it's there. In binary, you cannot represent the number 0.7. So if I was to multiply this by 10, you get 700. What would you get here? So let's multiply by 10. And multiply by 10. Doesn't matter where we do it. That number doesn't exist in a computer. A computer has no binary representation for that number. So where is that number coming from? Well, it's coming from somewhere else. It can't be stored in memory. So what is stored in memory must be a token that says, ooh, this should be this, but we're representing it as this. If you get my idea. We're being lied to. The memory of the computer isn't 0.7. It can't be. That's a physical impossibility, not a computer problem. Because we're using ones and zeros. There are certain things that binary cannot record. And that's interesting. So how's it done it? I think it's a tokenization idea, probably. And that is why modern computers seem to be able to calculate. But this pulls up a new problem, or a new thought. I don't like problems, I only have solutions. This pulls up a new thought of, well, if I have this 0.7 in memory of the computer, and I know it can't be stored as 0.7 in the memory of the computer, what happens if I leave that there, and then later on in the program, 1 mile down the road in the code, 1,000 lines later of code, I need to use this in another calculation. Will it still be 0.7? Or will it be whatever approximation binary can make of it, which is 0.699999, by the way. That's the approximation that binary can record. So what will I get back? Will I get back from memory 0.7, which is the accurate calculation, or will I get back from memory 0.699999999 recurring? And the answer is I don't know. That's the solution. You see, that isn't a problem. The solution is I don't know. And why would the computer care which one I got back? There's no point of reference. There's no calculation to get to the 0.7 at that instance in time. Unless it's been tokenized and flagged as a 0.7, then what comes back from memory in the computer is going to be 0.69999 recurring. I can't put that. I've got a feeling if I did the full experiment, I'd just be wasting my time because it would come back as 0.7. My theoretical brain says it would be stupid for them to leave it in memory as 0.699999, although they could, and then detect whether it's a 0.6999 and correct it to 0.7, because that could cause a different error, couldn't it? That if the value was actually 0.69999, you don't want it to be corrected back to 0.7. So they'd have to tokenize it as 0.7, would have to be a token. How many of these tokens would you need? An awful lot. There's an awful lot binary cannot record in the sub-decimal place, I'm going to call it, below the first decimal place. There are a lot of numbers you cannot record in binary. They just don't exist. Which is interesting. In its own right. Numbers that don't exist in binary. Google's your friend. Oh, I've got all this lot on it, haven't I? Ooh. Let's go to this page then. We'll give ourselves a different page, shall we? Oh, that's pretty. Real numbers that do not exist in binary. There we go. Why can't decimal numbers be represented exactly in binary is what I'm trying to get at. We'll just go with the first thing. Well, this isn't very good. Decimal numbers can be represented exactly if you have enough space, just not by floating binary point numbers. This is what I'm trying to say. This is an answer, and it also agrees with the title. In floating point, numbers change their property. So this isn't very good. It's not going to give us the kind of numbers. Yeah, okay, that's a pretty bad explanation of it all. Data representation. Okay, so it tells you how it's represented. Yeah. Okay. So 7 would be 4, 2, 1, which is 1, 1, 1. That's okay. But a half, a quarter, etc. Yeah, we're okay. But that's the point there. It's a half, a quarter, where it's as 1, 2, 4. It's 1/2 quarter. And that's why you've got to be very careful in binary when you're doing calculations. 0.5, 0.25. So the yeah, that's correct. So how do you get 7? You need that, and you would need 0.2. Well, the closest you can get to 0.2 is by having the next one along as a 1. You can't actually get to 0.2, because every time you get to the next one, it's a square of that one. 0.5 times 0.5 is 0.25, correct. 0.25 times 0.25 is the next slot where you can put a 1. So as you can see, you can never get to 0.2. So you can never represent 0.7. You can try it out yourselves. In fact, you can write a program to show this. Just by, so 0.25 times 0.25. Let's do that. We've got a calculator here, so let's do 0.25 times 0.25. So that becomes a 5. That becomes a 2. 5. So you're being lied to here at this point in time. The computer is lying to us, which is interesting. So it's 0.625. So we would need the next one along as a 1 as well. This is to try and get 0.7, because 0.75 would be too high. We need lower than that, so we have to put the 1 in the 0.625, and all we do is add them up. So it'd be 0.625 plus whatever we put in the next slot. What will we put in the next slot? Well, 0.625 times 0.625, what does that result? Is if those two added together are greater than 0.7, it's a 0. If it's less than 0.7, it's a 1, because we want them to be added up. And if you go by those rules, you'll never get to 0.7. And you can do the calculation, and you can show the binary representation of 0.7 is inaccurate or can't be done. That makes it even more interesting. So they're not actually saying, okay, the result, are they? So which real numbers cannot be represented in binary? Blah, 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 blah. Oh, God, that's just a stupid post. Thank you. Yeah, they've got the 0.75 again, which is useless to me. I want the 0.7. There we go. Blah, 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 blah. Yeah, I know, we've already been through that. I want to know the actual numbers. Oh, well, they've actually given the equation, which is good. Nope, that's a book advert. Fantastic. So they're not going to tell me the numbers, which is what I've just asked for. It's just a repeat, isn't it? So all it's doing is repeating the same information, but it's not telling us the numbers. So as we can see here in a code example, if all of... Yeah, okay. It's not going to help us, is it? Why do computers use binary numbers? Because it's an on-off machine. That's a stupid question. Does not exist in floating point. Ah, here we go. So, why does 6 times 0.1 not equal 0.6? And that's because it can't be represented. Right, yes. Yeah, 0.3 times 0.6. Sorry, plus 0.6 here equals 0.9. So 0.9 is another one that can't be represented. That's what they're trying to say here. Why the heck they put it like that, I don't know. So the binary equivalent of 0.9, or... They're not actually doing 0.9 here, though. Take 0.1, for example. It's one of the simplest decimals you can think of, and yet it looks so complicated in binary. Well, no, it intrinsically goes on and on forever, because 0.1 cannot be represented in binary. But that's your problem. Or is that the solution? I don't know. To 1,369 places, yeah. But you can see how the pattern starts repeating. So it's a repetitive pattern. What you get is 0.0999999999, or you get something weird. Seems to be too many decimal places on it though at the start for 0.1. So I disagree with what they're showing. I think they're showing something different than 0.1. Looks a bit dodgy at the beginning there, doesn't it? I think they didn't mean to have those 3 zeros there. Whoopsie daisy. That would mean that the first line would then match up with all the other lines. Yeah, okay. Which is what I would expect. So I don't believe what I'm looking at here. That's the first thing. But the explanation is correct. Yeah, they're dropping it down, looking at it all. Yeah. So they are keeping this... I don't know how to do all of this maths. 0.1 in decimal. So if you take that and put it into decimal, you get that. It's too many. So you get to see the problem with mathematics in computer programs. What do? You can avoid the numbers that can't be represented. There's that, which is what I would do. But otherwise, there's nothing you can do, because computers work in binary. So that's why I said I know that it was lying to us. That number there, it's lying to us. That 0.7 doesn't exist. In memory. In the computer's memory, that 0.7 cannot exist. That's interesting, isn't it? Which is why I chose those two numbers, by the way, because if you notice, one ended with 3,5. And the other one just multiplied 3,5 by 2 to get a 7. All I wanted was a 7 in the result of the two numbers. So the two numbers that I chose for the experiment should not be able to be represented. So all I did is I would put a 3 there to get me 3, 5. And then I would put, I'd change those two around, wouldn't I? So it'd be 5, 2, 0. So 2 times 3, 5 is a 7. And I wouldn't want anything else added on to it, so I put a 0 in. So 2, 3, 5. 5, 2, 0. Means that I'm going to get a 7 in the result, which I know can't be represented. And yet, that's not what I got. Huh? Did I just choose the wrong numbers? It looks like it, doesn't it? We have to keep them the same number of numbers. Change that for a 1 then. You can play around with numbers all day. Alright, let's just get rid of that. Let's have a look at the result. That's better. There's no 7 there. It's because of the addition, isn't it? I'm taking out the 7. So we'll bring you down to a 1 as well. Ah. Actually, no. I'm just going to take the 1 off. There we go, we've got 7. That's what I was after. So that's 47,000.47. Now I know that that cannot be stored as binary. Or possibly it can. And we come down, if we keep these two the same, which we should do really for the experiment. Yeah, 7,000.7. So I know the second one's wrong. That can't be stored. What was the other one we said? 0.9? Which is 4.5, isn't it? Let's see if they've got that one as well. Yes, they have. They catch that one. Well done, computer. People. Makers of computers. They know they can't store the numbers, so they have to do something different. Interesting. Do they recalculate the number then? They can't do. What they could do is take the fraction and store that. So 0.9 can be stored as 9 divided by 10. And then when you want to look at that memory location, it returns 9 divided by 10. Because that's two integers, which can be represented in binary. That's a possibility. Wow. It opens up such a new can of worms. 0.1. How do we get 0.1? I don't know. What multiplies by what to get 0.1? Is it 0.2 by 0.5? Yes, it is. So if that was not there, put a 0 on the end. 2 times that goes to 10. and then it shifts down. So we have to put a 0 on the end. Is that 0.1? Oh, no, it's not. So we need to shift it down by 10. That becomes that. That becomes O there. Let's try that one. There you go. 8,000 equals 0.1. Does it? Really? Do you think so? Correct. 80,000 does equal 0.1. But you can see how we've destroyed the symmetry. That's an interesting result, that one. Why does that one work? Okay, let's take the zeros off the end and simplify it. Okay, simplified it down to the least number of numbers I can use. So 1,000 equals 0.1. Hold on a minute. That's why it was happening in a large screen. 80,000 equals 0.1 and 1,000 equals 0.1. That one I can accept. That one, ooh, is an error. And the error is where I put the zeros. So if I put the zeros behind here, do they have to go in front here? Because it's reflected, isn't it? It's a reflectivity equation. That's interesting. I'd need to think about it more. But I cannot state that that is true. Because I haven't thought about the reflection around the decimal point when I'm typing in the numbers. I haven't adhered to the equation. So I think that's my mistake rather than the computer's. Good. But you can now see the problems of doing the experiment. You can't just type in numbers at random. You have to really think about it. And it comes up as 5 to e to the minus O2. And that's how they're storing it. So it tells me. Cool. That's even funnier. Now, I didn't know that. So it's actually telling me here how it's storing it in memory. So it's storing it as an integer and then multiplying it by 10 to the minus 1. Okay. I thought I'd share this with you because I wanted to do the experiment to find out whether modern day computers are cheating or not. And they are. Is the answer? They are cheating. There's an awful lot of numbers you cannot represent in binary, especially when it comes to real numbers which have decimal places, because certain numbers don't exist in binary. The multiplication experiment. If you try it today, you cannot find the errors because the people who have manufactured the maths chip on your CPU have altered the mathematics in a way to cover up the fact that the computer can't do the calculation. That's really interesting. So your computers are lying to you, peeps. It's also the reason why when you're doing 3D graphics, you get errors. Because the calculations, you can't cover up every single number that can't be held in binary, I don't think. Unless they found a way to do it, an algorithm to do it. They might have done. Okay. Thought I would share my thoughts on multiplication and how you can experiment with it. And how deep that experiment starts to go down a rabbit hole as soon as you start doing it. And it's something that you thought, this video isn't worth watching. It's not going to prove anything. No, it doesn't prove anything, you're quite right. But what it does say is something has happened to computers. If I had tried this experiment in 1985, it would have just said error. Interesting. You have to find an old computer that works and write the same program and try out the numbers and find out what it does. Old calculators had the same problem. So, yeah, there's that. Interesting. Just thought I'd share that with you. There's no conclusion to this one, except I know what's going on and it's not really being taught very well unless you're trying to manufacture mathematics chips, I suppose. Then it will be taught to you. Definitely. I'm not sure how that goes. What is my conclusion from this experiment? The conclusion is that modern computers lie to us. That's my conclusion. And on that happy note, yeah, have fun. Now you know what I do on my time off.